Hi everyone, in this video we will see how to solve second order homogeneous linear differential equations of this form, that is of the form ay prime prime plus by prime plus cy equals to 0, where a, b and c are constants. Now to solve this equation, we assume that y equals to exponential mx and y prime equals, if we differentiate this guy, we have m, so m exponential mx, and then we differentiate the second time, y prime prime gives us m squared exponential mx. That is, if we differentiate this, we get m, so m times m gives m squared. Now we substitute this into the given equation to give us a, then y prime prime is m squared exponential mx plus b, y prime is m exponential mx plus c, y is exponential mx equals 0. Now, and this, if we look at this carefully, you will observe that exponential mx is common to all three terms, so we can factor out exponential mx. So this implies that exponential mx, we can factor it out, and we'll have am squared plus bm plus c equals 0. Now we have the product of two terms giving 0, so it implies that either exponential mx is 0 or this guy here equals to 0. But exponential mx is never equals to 0. This guy is never equals to 0. The exponential function can never be 0. So it means that am squared plus bm plus c equals 0. Now this equation is called the auxiliary equation or the characteristic equation. Now this is a quadratic equation, and if we solve this, we obtain m equals to minus b plus or minus b squared minus 4ac over 2a. And this is a solution to this our auxiliary equation. Now this solution gives rise to three cases. The first case is when the roots are real and distinct. That is where b squared minus 4ac is positive, when this guy is positive. And then we have case 2, real and repeated roots, where b squared minus 4ac is equal to 0. And the third case, complex roots, where b squared minus 4ac is negative. Now we'll look at examples to illustrate these three cases. So let's see the first example to illustrate case 1. Now, if the roots of our auxiliary equation is, if they are m1 and m2, then the general solution of the second order differential equation is given by y equals to a exponential m1x plus b exponential m2s, where a and b are arbitrary constants. Now let's see an example to illustrate how to do this. Now we look at y prime prime plus 2y prime minus 15y equals 0. If we compare this equation with the general form of the second order differential equation, we see that a here, our a is 1, b is 2, yc is minus 15. And so we can now form the corresponding auxiliary equation to this differential equation as m squared plus 2m minus 15 equals 0. This is our auxiliary equation. A is 1, b is 2, and c is minus 15. So to solve this quadratic equation, we will look for two numbers such that when we multiply them, it gives us minus 15, and when we add, gives us plus 2. So those two numbers are minus 3 and 5. Minus 3 times 5 gives us minus 15. Minus 3 plus 5 gives us 2m. So we can now have m squared minus 3m plus 5m minus 15 equals 0. Now if we factorize this, we have m minus 3 plus 5m minus 3 equals 0. Now this implies that m minus 3 equals to 0, or m plus 5 equals 0. And this implies that m equals to 3 or m equals to minus 5. Now these are the two distinct roots that we got after solving our differential, the auxiliary equation that is corresponding to this guy. Now, so our general solution will now be y equals to a exponential m1x, and our m1x is 3, our m1 is 3, plus b exponential m2. m2 is minus 5, minus 5x. So this is the general solution to this second order linear homogeneous differential equation. In the next video, we will look at case 2, which is the real and repeated root. I hope you enjoyed this video. If you have any question, you should drop them in the comment section. Thank you.